Today I'm going to describe the most common way of looking at the photoelectric effect. So this is your most common setup. You have a battery at the bottom here, and you have a light that's shining onto a metal plate. This metal plate is, because it's getting a light shone on it, is getting this energy from the light, and therefore it shoots off via the photoelectric effect. It shoots off these electrons. The electrons start with an initial velocity, which means they start with an initial EK, initial kinetic energy, because they start with an initial velocity, and they start with a zero electric potential energy. Okay, so they're flying here. At the beginning part, they start with that EK, but they have zero potential energy, and then they fly all the way. The whole time they're getting dragged down. Sort of, you can think of it like gravity dragging it down, but instead of gravity, it's your electric field. So instead of you throwing a ball up and asking what height does it get to, or what speed was it when you threw it, it's you're just looking at the electric field instead. So then at this point, right before it reaches the second plate, that's where the velocity is zero. So that velocity equaling zero is where you can say that this voltage here, the electric field, this stopping voltage, has made the electric field in such a way that the potential electric field energy at that point, getting sucked back to the initial plate, is equal to the initial starting potential, or the initial starting velocity. Okay, so in terms of equations, we're going to look at it like this. This voltmeter, just basically it's saying that we can change the voltage to the battery in our scenario, and whatever we change it to, we're going to measure it. Okay, now we've got light. Let me just draw streams. There you go. Light incident on our plate from our big lamp here. Look at that beautiful lamp. Okay. And then it shoots off electrons. Okay. And as we talked about today in class, there's going to be sort of different levels of electrons. Some are going to get right close up to it. Others are going to get a little bit further. Some are just going to get a little bit, just pretty close. Okay, so they're not going to look exactly like that, but I'm just saying it just to make a point. Okay, so at the beginning of the situation, how about I use a different color here? At the beginning point A, comparing to the end point B. So, well, actually, not. Point B is the end point of the electron, like where it stops moving forward and starts moving backwards. Okay. So at the beginning point, we can think about it as it starts with an EK. Okay. So this question is just a conservation of energy. E in equals E out. Well, better way to look at this. So I'm going to change these things around. E in is going to be this photon energy. Okay, so the photon energy is EF, or you can write it. This is still a photon. E in. Okay. HC over lambda. That's another way of writing it. Now, E out is going to be EK, the initial kinetic energy, plus the work function that it took to pop out that electron initially. Okay? So those are the two things. So we've got, on this side, I'm just going to call it HF from now on. Either one works. And on this side, we've got EK plus W. Well, EK at point A is the same thing as the potential energy that it has at point B, the electrical potential field energy. Okay, field energy meaning that at point B it's being sucked backwards back to point A. Okay, so that field energy is what we call VQ. Okay, so this is why we can start doing all of those calculations with this scenario, is because we can measure this voltage at the bottom, we're able to then put it into our equation, and this Q here is the elementary charge, or it's the charge of the particle, but in this case, since it's only one electron at a time, it's going to equal 1.6 times 10 to the negative 19 coulombs, right? So we know a lot about this. So the only thing that we don't know is the F, frequency of the light coming in, but depending on your light, you might know that. And W. W here, the work function, is a property of work function is a property of the metal. Property of metal. So depending on the metal, it's more tightly grabbing at the electrons and holding it in. Some metals are willing to give away electrons. Some metals really hold on tight. And that's basically the whole photoelectric effect, and just an overview of it. This simulation is really, really nice because you can see these electrons getting so close to the end and then stopping and turning around. So that's exactly where you want it to be. And then you get this voltage here. This is the stopping voltage at the bottom. And you figure out the wavelength of the light. And now, from all the data that's on the simulation right now, you can figure out the work function of your metal.